that I'm going to have you guys do some problems similar to this today is just focusing on differential equations, and then we will focus on slope fields on a different assignment. So, so first what we're asked to do on these problems is to find the general solution. So we're given a differential equation. Remember, a differential equation just means that it has a derivative in the equation, so this does. So we're going to find the antiderivative, and on some of these you're just going to have to think of what function, if you take the derivative of that function, gives you secant x times tangent x. And hopefully you remember that the derivative of secant x is secant x tangent x. So when you are solving this, we would get y equals, and we're going to have a secant x, because the derivative of secant x is secant x tangent x. And then the derivative of, the antiderivative of e to the x is just e to the x. And then because there could have been some constant, we have to include the constant. So you can always double check your answers. If you take the derivative of this, the derivative of secant x is secant x tangent x. Then we would have minus the derivative of e to the x is e to the x. And the derivative of a constant is 0. So then you can verify that that would work. On the next problem, you may want to first think of this as dy dx equals 1 over x minus x to the minus 2. Because when you do the antiderivative, we usually like it to be with a power, and you might wonder, well, why didn't I write this as x to the minus 1? Because when we should know a function, that there is a function, if you take the derivative of that function, you get 1 over x. And that function is ln x. So when you are looking for the general solution, the derivative of ln x is 1 over x. So we're going to have an ln x here. And then if you do the antiderivative of this, you're going to raise the power by 1. So it's going to be x to the minus 1. But remember, if you take the derivative of this, you're going to divide by the new power, which is going to change the sign here. This is going to be plus. So we can just say this is ln x. Oops, I forgot something. Plus a constant. But I'm going to rewrite this as y equals ln x plus 1 over x plus a constant. And when you look at this right here, this is actually a hint when they tell you that x is greater than 0. Because the reason that has to be true is, remember, when you do natural log or any kind of log, then the input value has to be greater than 0. You can't take the log of 0 or log of a negative. So this is kind of a hint that your answer involves logs when you see something like that. So kind of pay attention to that. But anyway, this would be our general solution. All right, also finding a general solution on this one. So when you are thinking about this, now I know that the derivative of e to, when I'm taking a derivative of e to the something, I get e to that same something, and then the chain rule. So notice, we know that our antiderivative is going to have to involve e raised to the power. So I'm going to start with this idea. So it's a little bit of guessing and checking. We're going to have another way we talk about later. But let's suppose I make a guess, and I think, well, I think the derivative is going to be e, or I'm sorry, the antiderivative is going to be e to the sine t. Well, now take the derivative of this. If I take the derivative of e to the sine t, I get e to the sine t times the derivative of sine t, because it wasn't just a t. So notice that would take me back to this cosine t. So this is actually the antiderivative right here, but I need plus a constant. And again, if you double check this, if you were to take y prime, you would get e to the sine t times the derivative of sine t, and the derivative of a constant is 0, so you get what we needed to get. So you can always double check your answers. On number 10, again, notice that if I take the derivative of sine, I'm going to have cosine. So I'm going to make a guess, and I'm going to say I think that y equals something that's going to involve like sine u to the fourth power. Now, we're going to be talking in the next section about some other ways, so you're not just guessing, but right now they're going to be functions you're familiar with the derivatives, and so there might be a little guessing and checking. So I make a guess, and then I think, okay, maybe this is it. And then I say, well, wait a minute, y prime, I'm going to double check this, is going to be 4 times sine u to the third power times the derivative of what's inside. The derivative of sine is cosine. So I would get that, which is what I started with. So then that tells me I'm right. I just need plus a constant, and this would be my answer. Okay, so again, a little bit of guessing and checking, but you can handle that. Now this one, I'm told, is an initial value problem. So I'm not just finding the general solution, so I can go beyond having a plus c, and I can actually figure out what that constant is. So that's what we're going to do on this one. So I start off the same way with the antiderivative. So y equals the antiderivative of 2e to the x is 2e to the x. The antiderivative of cosine is sine. Okay, so think about that. And you double check it before you go on. The derivative of 2e to the x is 2e to the x. The derivative of sine x is cosine x, so the sign doesn't need to change or anything. And then I have plus a constant. Now I'm going to input my value. So y is 3 when x is 0. And now I can solve for my constant. So anything to the 0 power is 1, so 2 times 1. Sine of 0 is 0. So that means my constant is 1. So then now my initial value problem, I can actually get the explicit solution, is what this is called. So this, instead of a general solution, this is an explicit solution. And that would be my answer for this problem. Okay, so when we take a look here, I'm going to look first at my differential equation. I know that the derivative of tangent is secant squared, so that tells me something there. And then this, I'm going to probably rethink and write this as x to the 1/2 power. So if I rewrite this as dy dx equals 5 secant squared x minus 3/2 times x to the 1/2 power. So then y equals 5 tangent x, because we said the derivative of tangent is secant squared x. And then here, I'm going to think about this now. I'm going to increase the power by 1, which is going to take me to x to the 3/2. And since they have a 3/2 here, that would be dropping down here, and it's going to stay negative. So I can see that when I take the derivative of this, I would get 5 secant squared x minus 3/2 x to the 1/2, so that works. So I'm going to have my plus c. Again, notice how every time I do the antiderivative, I check it by finding the derivative and making sure it matches my differential equation. So now I'm going to plug in my initial value. So I'm letting y equal 7 when x is 0. And solve for c. So tangent of 0 is the same as sine of 0, because remember tangent theta equals sine theta over cosine theta. So keep that in mind, that identity. So whenever sine is 0, tangent is 0. If cosine is 0, then tangent's undefined. So since sine of 0 is 0, then tangent of 0 is also 0. And 0 to the 3/2, of course, is 0. So we get that c equals 7. So now I go back to my explicit solution. So we have 5 tangent x minus x to the 3/2 plus 7. And that is my solution. Okay, actually, we do have a condition that we have to think about, and it kind of ties into what I had mentioned here, because this is not continuous everywhere. So we do have to think about our discontinuities, and we have to put a stipulation or a domain values. So because tangent theta is undefined when cosine is 0, so if you think about when cosine is 0, cosine theta equals 0 when theta is pi over 2 or negative pi over 2. Actually, it's any odd multiple of pi over 2. Think of the unit circle. Anytime it's at the top or bottom of the unit circle, cosine is going to be undefined, or cosine is going to be 0, which means tangent is undefined. So we're going to have to put this stipulation. Now we know we're talking about when x is 0, so that tells me which part of the function I want. So we need to state that x is between negative pi over 2 and pi over 2. So that would have to be a restricted domain, because I know that tangent of pi over 2 is undefined. I know that tangent of negative pi over 2 is undefined, which means it would be discontinuous at those spots. And since we know x is 0, then I know this is the piece, the continuous piece that I would be talking about. So you do have to think about that as well. Okay, so this problem is actually not hard, but it's going to be a little bit confusing. It's solve the initial value problem using the fundamental theorem of calculus. Your answer will contain a definite integral. So basically, I'm going to tell you what the answer is, how you get it, and then I'm going to explain to you why that works. So we're going to let u equal the integral from 0 to x of the square root of 2 plus cosine t dt minus 3. And I want to explain to you why this works. Now, we're given an initial value problem. We know that if we want to do the antiderivative, then we take an integral, because remember, an antiderivative is like an integral. So we're taking the integral of this expression. And then when x equals 0, so watch what happens if I were to evaluate, I could think of this as u of x, if I were going to, like I could use this notation. So if I were to evaluate when x equals 0, I'm going to get u equals the integral from 0 to 0 of 2 plus cosine t dt minus 3. But this whole thing, remember when the limits of integration match, this whole thing goes to 0. So I get 0 minus 3, which is negative 3. So then I've just satisfied this condition right here. So you can see that it works. So let's now take this and go back to what I have up here and find the derivative. Switch colors here. Okay, so if I were to go up here and I want to find du dx, so remember what I'm doing is I'm taking the derivative of an integral, and I switched to t. This is like a dummy variable. So I'm taking the derivative of an integral. This is why they mention it's the fundamental theorem of calculus. You're taking the derivative of an integral, got a constant at the bottom, an x at the top. Notice what's going to happen. I'm going to end up with, because derivative, I just plug in an x, and so I get 2 plus cosine x, and then this minus 3. So you can see that it works, because I do get, I'm taking the derivative of this whole thing, not just that. So this derivative of constant is 0. That needed to go away. So you can see that it works, and I get that back. So then what does this mean when you're doing a problem? Well, this expression right here is going to be the integrand inside your integral. Whatever this is, when they give you the initial condition, the x value, whatever that is going to go down here as your constant. And then whatever this is going to either be, if it's positive or negative, depending, it's going to be added or subtracted to the integral. And that's going to be your answer. So, and again, double check it. Once you plug in the pieces, but that's where those pieces will go. And once you plug in those pieces, you can double check the derivative and make sure that you get back what you are started with, your differential equation. And then also keep in mind how I'm using the fundamental theorem of calculus. I'm taking the derivative of an integral. That's what the fundamental theorem of calculus part 1 is all about. So this should help you with your first assignment, and then we will do slope fields a different day.